Hello and good day. My name is Abdurrahman Hassan Abdullah and I'm going to present Radioactive Tracer. Radioactive Tracer logins is the most commonly used technique for determining injection profiles in water injection wells. Its applications include obtaining injection profiles, check for channeling behind pipe, and also locate tube encasing and backer leaks. Radioactive trackers play a crucial role in interwell studies as they provide valuable insights into the dynamic flow behavior of a reservoir. By tagging injection water and analyzing samples from production well, we can reveal important information through response curve. These informations include detection of high permeability channels, barriers, and fractures. These trackers help us identify areas of enhanced or restricted flow, providing valuable information for the reservoir characterization and management. We can also detect communications between layers, evaluating of the fraction of the injection water reaching each production well, determinations of RTDS, indication of different satisfactions in the same layer, determination of professional flow directions in the reservoir. There are two radioactive tracer methods that are currently being used. The first one is the tracer loss method, and the second one will be the velocity shot method. The tracer loss method is where a single slug of a tracer is injected into the well bore above all the zones of the fluid loss, and then the concentration is measured as a fraction of a depth by passing a gamma ray detector repeatedly through the tracer as the tracer slug moves down in the well bore. For example, as you can see in the picture on the top left, we imagine as we have a liquid in a pipe and we want to find out where the liquid is exiting from the pipe. And in order to do this, we use a special substance called tracer that you can track as it moves through the flow. And for our example, we take the measurement at 3 different points. The first point will be this one, D1, the second point will be D2 and D3. And this is where our fluid is lost or the fluid is exiting from the pipe. The first measurement is taken above the point where the liquid exits. The second measurement is taken when half of the tracer substance has passed the exit point, as you can see. The third measurement is taken when the entire tracer substance has passed the exit point. The distance between the first and the second measurement represented the portion of the trace substance that is still before the exit point. Since only half of the trace has passed the exit, we can say that there has been some fluid loss in this distance. The distance between the second and the third represented the portion of the tracer substance that had already passed the exit point. As this section is half of the size of the entire tracer, we can say that there has been more fluid loss in this distance. Now let's move to the velocity shot method, which is the second commonly used technique in tracer studies. This method provides insight into the fluid velocity and volumetric flow rates within the well bore. The key aspect of the velocity shot method involves measuring the transmit time of tracer slug between 2 points in the well bore. Typically, this is done by replacing gamma ray detectors at these points, although sometimes the ejector and the gamma ray detectors are used. So after measuring the transit time, we can calculate the fluid velocity, and then the volumetric rate is determined using the average velocity and the cross-sectional area between the detectors. So moving on to the recent applications of radioactive trackers in determining fluid movement and in adjacent to the wellbore. Water entry determination. Reliable and quantitative determinations of water entry can be obtained by correlating data from the three surveys. The first one will be the temperature survey, the velocity profile survey, and radioactive conditioning survey. These surveys help identifying the boundaries of the fluid movement and determining the location and extent of water entry intervals. Then we have temperature survey. A temperature survey is conducted through the Brodesian interval to aid in identifying fluid movement boundaries. Temperature variations can indicate the presence of different fluid and their flow patterns. We also have velocity profile survey. This survey involves using a tool arrangement with radioactive isotope emitter and gamma ray detector. Then lastly, we have radioactive condition survey. Now we move the field application of radioactive tracker. The Fairway oil field is a natural reservoir that was undergone gas injection for enhanced oil recovery. They wanted to optimize the gas injection process and also to improve oil recovery efficiency. Then radioactive trackers were implemented. Prior to the tracer program, the field exhibited complex fluid flow patterns with irregular gas sweep configurations and uncertain displacement fronts. So the primary objective was to understand the behavior of the injected gas and the interaction with the reservoir fluid to improve the design and implementation of gas injection strategy. Overall, the application of radioactive tracker in Fairway oil field facilitated a better understanding of fluid flow pattern, influenced injection strategies, and contributed to the overall success of the gas injection project. Okay, moving on to the advantage of radioactive tracker includes high sensitivity and detection capabilities, non-intrusive and non-destructive nature, versatile applications, quantitative analysis, cost-effective and efficient. This is the cost of Fairway Tracer project that we discussed earlier. The total cost of the Fairway Radioactive Tracker project consisted of 13 gas trackers and 2 water tracers is about 40,000 USD. Individual cost per tracer on generally about 1,000 to 2,000 USD dollars. Analytical costs are approximately $40 per sample, although in conclusion, radioactive isotopes have been field tested and proven to be reliable tracer at Fairway. The source of breakthrough can be determined by radioactive trackers, provided adequate samples are taken. The configuration of displacement front, variations in sweep patterns, and fluid movement in general can be detected by radioactive tracker techniques. Radioactive tracer can indicate whether injected gas is going into the solution or mixing immiscibly with the reservoir oil, provided reservoir pressure is above saturation pressure. Multiple tracer injections at a single source can be used to measure the relative velocity of injected fluids behind the displacement fronts, improve knowledge of reservoir flow conditions, and fluid displacement mechanism can be gained through both qualitative and quantitative applications of radioactive tracker techniques. And lastly, this is the reference. Thank you so much.